Hi, my name is Cameron Zuckwitz Ray, and today I'm going to be teaching you what is known as Newton's method and how to apply it. So, when is this used? Newton's method is used when we're trying to approximate the solution to an equation when the function f of x is equal to 0. So, using this method, you can find where your function crosses the x-axis, as this is synonymous with the root of a function. Using Newton's method, we can try and estimate a solution to an equation or function using tangent lines. And we will evaluate the tangent lines when f is close to 0. So we can try and look at this visually through the use of a graph. So say we have this function. And this function is y is equal to f of x. Now, we want to try and find this root. Now, in order to do so, the first step is to make an initial guess, one that we can reasonably say is close to the root or the solution. So let's say our first guess is going to be right here. And here we can say x sub 0, f of x sub 0. And we're going to follow this down to our x-axis. And we're going to label this x sub 0. That's our first guess, although as you can see, it is still far from the root that we want. So, using the tangent line, you'll find another root. It may look something like that. So then we'll go up from this, and we're going to have our second reasonable guess using the tangent line. Now we can label this x sub 1 of f of x sub 1, and here we can do x sub 1. Now that's our second guess. Now, since we're still far away from our sought out root, which is right here, we are going to use another tangent line. So we're going to evaluate the tangent line at x sub 1. So we will then use another tangent line. And now we're increasingly getting closer to our sought out root. So this point we can label this x sub 2 of f of x sub 2, x sub 2. Now we're incredibly close, so we're making one more tangent line. And as we can see, that goes through our sought out root. So x sub 3, f of x sub 3. So this is just a visual way of looking at Newton's method and how we can use tangent lines in an initial reasonable guess in order to find our sought out root or where the function crosses the x-axis. Now, the formula for this is going to be x sub n plus 1 is equal to x sub n minus f of x sub n over f prime, or the derivative of x sub n. And that is going to be the main formula for Newton's method. So what are the steps? I'm going to write down the steps. Now, Newton's method can be a tedious process, so understanding each step will make it much easier. It's a repetitive process as well. So to start, we're going to make an initial guess in which we can reason is close to the root. So our first step is to make an initial guess and we're going to try and get as close to the root as possible. Okay, and we can see we did that through here. We have x sub 0 of x sub 0. That was our initial guess. Now, once we find an initial spot on the function, we find the tangent line. And this allows us to use our knowledge of linear approximation. So, 2. We're going to use the tangent line to find a closer point. Now, if we want to look at this visually, we can see we did that by finding the tangent line of x sub 0, which would give us this, and then from x sub 1, we found a new spot, and we repeated the process with another tangent line, and so forth. Now, we're going to continue to use step 2, or finding the tangent line, until our tangent line converges with our desired point on the x-axis. And this will make sense later. So step 3 is to continue step 2. Until our tangent line, we'll make that TL, converges with our desired point. Or the root. Okay, and for a sort of proof for this method, we can look at the mean value theorem, because the mean value theorem ensures that there's a root within the function x sub n, then it also exists within x sub n plus 1. And if we recall what we know about the mean value theorem, it states that for a function that is continuous on a through b, there must be at least one point in which the tangent line is parallel to the secant line through its endpoints. So now let's look at a quick example of how we can use Newton's method. So in this example, we're going to use the simple function x to the 7th minus 1,000. And we want to find the root or the solution to this through 8 decimal points. So our first step, we're going to plug this equation into our formula. So we are going to have x sub n plus 1 is equal to x sub n of f of xn. So we have x to the 7th minus 1,000. And then we're going to have f prime, so the derivative, so using the power rule of 7x sub n to the 6. Now, if we wanted to draw a graph for our function, it would look something similar to this. So we know our x-axis, our x-intercept is going to be somewhere between 2 and 3. So let's continue on with our steps. So we've plugged the original equation into our formula. Now we need to find our x sub n. So we're going to say that x of 1 equals 3. So we're going to do x n plus 1. So x of 2 equals x of n. We just said x1 equals 3. So we're going to do 3 minus, and we're going to plug in 3 for our x of n. So 3 to the 7th minus 1,000 all over 7 times 3 to the 6. And if you plug this in, we will get 2.76739,173. Okay. So now we're going to repeat this process, but adding 1 onto our x because x of n plus 1. And we're going to repeat the process, just like how on the graph we found a new point and repeated the process. We're going to do the same thing when calculating. Now we're going to have x of 3 equals, and we're going to use our previous solution because we're doing x of n. So now we're going to do x of 2, which we figured out right here. And x of 2 is going to, x of 2 equaled 2.76739,173. We're going to do minus, and we are going to plug this number back in for our x. Raise that to the power 7 minus 1,000 all over 7 times that same number to the power of 6. And this is going to give us 2.69008741. Okay, these are not the same yet, so we're going to repeat. So x of n plus 1, so 3 plus 1 equals 4, equals x of n, which is x of 3. We found that solution right here. 2.69008741 minus, plug that number into everywhere where there is an x of n, 7th, all over 7 times 2.69008741 to the 7th. Oh, maybe add to the 6 actually. And this will give us 2.68275645. These two are not the same, so we do it again. So x of n plus 1, so x of 4 plus 1 equals x of 5. And that would equals x of n, which is x of 4. We found that solution right here. We're going to plug that in. 2.68275648. Plug this number into everywhere the x of n is in our formula. Okay, and x of 5 equals 2.68269580. And we know that we're getting closer because our decimals are starting to look very similar, as you can see right here. So let's do it one more time. So x of n plus 1, x of 5 plus 1, x of 6 equals x of n, which is x of 5. We found that right here. 2.68269580. Plug that number in for all of our x's. So it's quite a tedious process, but just got to keep on repeating it. And we will get 2.68269580, which is the same as we got before. So they have converged. Now we can say it intersects the x-axis at x equals 2.68269580. And that is our solution with Newton's method. And we can put that right here. And that was our x.